Equilibrium expressions and constants is the next concept that we're going to cover. And so what you need to know about equilibrium expressions and constants is simply an equilibrium expression is used to calculate an equilibrium constant. So first of all, what is an equilibrium constant? Well, an equilibrium constant is just denoted by the letters Kc. And this ratio here is what is considered to be the equilibrium expression. So if I have a generic formula, chemical reaction I mean, like this one up here at the top, if I were to explain to you just kind of what this means a little bit, I've got reactants A and B reacting to make products C and D. Now you can see there's some little letters in front, and all that just represents is whatever the coefficient is in front of each of those substances when the reaction becomes balanced. And so when I write my equilibrium expression, there's a couple of things that I have to pay attention to. First of all, the concentration of any substance that goes in the equilibrium expression must be a concentration at equilibrium. So I can't use equilibrium, or I can't use concentrations that are not at equilibrium. And you're going to see questions where you will be given concentrations where it will say that these concentrations are not at equilibrium. You have to make sure that you don't stick those into the equilibrium expression and use them to calculate Kc, because you won't get the right answer. These expressions are only for equilibrium concentrations only. Now, for your concentrations, you have to raise them to the exponent of what their coefficient is. So you can see here for all of these, I'm going to write in an exponent for each of those substances. And so if this, for example, A has a coefficient of 3, then when I put its equilibrium concentration into the equilibrium expression, I have to raise that concentration to the power of 3. And so this just aids in our calculations to take into account that these reactions react based on ratios. And so those coefficients mean something, and they've got to be a part of our calculation. The next thing to point out is notice that the concentration of the products go on the numerator and the concentration of the reactants go on the denominator. And that's true for every chemical reaction. Anytime that you write a Kc expression, the concentration of the products goes on the numerator and the reactants go on the denominator. That's consistent throughout. Also, anytime that you have a substance with a state of matter within these reactions, you only include the substances that have states of matter of either gases or aqueous substances. So, for example, if D in this chemical reaction was a solid, then for my equilibrium expression, I would just omit D from the expression, which means that I wouldn't use D in my calculation at all, or any concentration that I was given for it. And that's consistent also throughout all equilibrium expressions. That's a rule that's hard and fast, and you follow it all the time. Only gases and aqueous substances go into the equilibrium expression. Now, if you take a look at this example down below here, what you'll notice is using this chemical reaction that I used in the previous video, and we've got the formation of hydrogen iodide here. And you can see that I've written the equilibrium expression for this reaction. Now, the concentration of Hi needs to be squared, and that's because the coefficient for it is a 2. The concentrations for H2 and I2 don't have exponents, and it's because they're just raised to the power of 1. And so 10 or 10 to the 1, those are the same numbers. We don't need to stick 1s in. It's redundant to do that. Now, in a question, you might be asked, what is the Kc expression? If you're asked what the Kc expression is, this is what you would write. If you're asked to calculate the Kc value, then what you would need is you would need the equilibrium concentrations for all 3 of these substances in order to do that. So if a question is asking you to calculate the Kc, then the question would need to give you what those equilibrium concentrations are. So let's say the question gives us the concentrations for these 3. The first one, let's say for hydrogen iodide, is 2.5 moles per liter. So the way that I'd write that in is just like that. I would put 2.5 moles per liter and then square that number in that format. And let's say that the question also states that the equilibrium concentration for hydrogen gas and iodine gas are both 0.35 moles per liter. So I would stick that in for both of those substances. Just like that. And then I can plug this into my calculator, remembering the rules of orders of operation, meaning that you need to do numbers that have exponents first before you go ahead and do multiplication and division. And so if I plug this into my calculator correctly, I should get 51. Now this is the Kc, the equilibrium constant for this reaction, given these numbers. And a couple of things to point out. First of all, you'll notice that Kc doesn't have any units. The reason it doesn't have any units is because I'm going moles per liter divided by moles per liter. So those units cancel out, and I'm left with a number with no units. Also, the value for Kc has a meaning. Because we're dealing with a ratio here, if my number on the top is larger than my number on the bottom, then that's going to yield a number that's greater than 1. And if I have a number that's smaller on the top than the number on the bottom, then that's going to give me a number that's less than 1. And so this is sort of this threshold where we say if a Kc value is greater than 1, then what does that mean? And what that means is that the products are favored. The next thing is if I have a Kc value that's less than 1, then that's going to mean that the reactants are favored. And so those concepts just really mean that if Kc is greater than 1, meaning the products are favored, it just means that in that chemical reaction, at equilibrium, that's the key, I have more products than I do reactants. Now, the thing that throws kids when it comes to this concept is that an equilibrium, a reaction that's at equilibrium doesn't mean that it has equal amounts of reactants and products. Remember our definition from the previous video. All that means when a reaction is at equilibrium is that the reactants are turning into the products at the same rate that the products are turning into the reactants. So the rate at which they're changing into one another is the only thing that's necessary for an equilibrium to be established. Well, one of the things, but equal amounts of the reactants and products is not one of those things on the list. I can have more reactants or more products at equilibrium so long as the amount of products that are turning into reactants is happening at the same rate that the reactants are turning back into products. And so that rate at which they're turning into one another is the key here. I can still have more of one than the other, and those rates still be equal. Also, one last thing that you need to understand as it relates to equilibrium expressions and calculations of equilibrium constants is that you could be asked to do a problem like this one that I've demoed here on the board, where you're given all of the equilibrium concentrations and you have to calculate what Kc is. What you could also be given is instead of this number being asked to be calculated, let's say that they give you the Kc value of 51, and then they ask you what is the equilibrium concentration of hydrogen iodide, for example. And so just doing some simple algebra, you can again write your equilibrium expression, plug the numbers in that they do give you in the question, like 0.35 moles per liter for both hydrogen and iodine, and then algebraically solve for the concentration at equilibrium for hydrogen iodide, just as a sample example of what that would be. So that's what you're expected to know as it relates to equilibrium concentrations, equilibrium expressions, and equilibrium constants. Thanks for watching, everybody. We'll see you in the next video.